Hey Raiders, let's take a look at a really simple forces Newton's laws of motion scenario. So the scenario we're going to take a look at, a 10 kilogram box is pulled across the floor with a force of 100 newtons. If the friction force resisting the box's motion is 30 newtons, what is the box's acceleration? So force is a vector quantity, so direction matters. So the first thing you should do anytime you're going to analyze something from the forces perspective is draw a free body diagram showing all the forces that are acting on the object and just sort of a big picture diagram to begin with. So here's our 10 kilogram box. Now terminology wise, we have to distinguish between mass and weight. In everyday life, these terms can be used interchangeably, but in the physics world, they have definite specific meanings. Mass is the amount of matter something has. That doesn't change whether you're on Earth or on the moon. But weight is the effect gravity has on an object's mass. So because the moon being so much smaller than the Earth, the force of gravity on the moon is only about 1/6 of what it is on Earth. So if you went up to the moon, your mass would be the same, but your weight would only be about 1/6 of what it is on Earth. All right? So the first thing we have to do on our free body diagram showing all the forces that are acting, we can figure out what the force of gravity is exerting on this 10 kilogram mass. So we can label it F sub g for force of gravity, or if you prefer, F sub w for force of weight, doesn't make a difference. But the bottom line, the way you find the weight of anything, you take the mass in kilograms, using the metric system. Kilograms is the base unit of measurement for mass. You take the mass in kilograms and you multiply it by the effect of gravity it's experiencing, 9.8 meters per second squared. Now notice, while force is a vector quantity and direction matters, I did not include a negative sign for gravity, even though it does pull down. And that really just is consistent with how we communicate in everyday life. Someone doesn't say they weigh negative 200 pounds, they just say they weigh 200 pounds. So same thing here. In isolation, when we're figuring out the weight of this box, we would just say it's 98 newtons. Once we start doing some calculations with it, then direction does matter. So then at that point, then we're going to be doing direction does matter. Then we will use positive and negative signs for calculations. Right? And then in response to that, we know that the box isn't going to go right through the floor. So obviously the floor has to push back to cancel that out. And so that's what we call the reactionary normal force, F sub n. And so it's not F sub n for net force, which we'll also talk about, it's F sub n for normal force. And if you think about this logically, we know the box isn't going through the floor, so the weight's not more than the normal force. And if the reactionary normal force of the floor pushing back was more than the weight, it would launch it up in the air. Obviously that's not happening. So really the only thing that's left is the normal force, the reactionary force of the floor pushing back against the box, is that it's got to be equal and opposite. So that's 98 newtons. And we're pushing with a force of 100 newtons. So you could call that force push, but generically it's called F sub a for applied force. So the applied force is 100 newtons. And friction always opposes motion, so we'll call that F sub f for force of friction. So at this point, now we're ready to use Newton's second law. Newton's second law says that the net force acting on an object, the overall combined effect of all the forces in whatever direction you're talking about, is going to be the product of the object's mass times its acceleration rate. So remember, direction matters, and we've already learned that perpendicular vectors act independently of one another. So since we're focusing on the horizontal or x motion here, the vertical components of the force of weight going down and the normal force going up, they're perpendicular to the line of motion, so we can ignore them because no component of those vertical forces is playing a role horizontally. So at this point, even though there's 4 forces in our free body diagram, the only ones we include for net force is F sub a applied force plus the force of friction. They're going to battle it out to see what happens here. And collectively, they're going to make this 10 kilogram mass accelerate at a certain rate. So our applied force is 100 newtons. Now we're going to take into account direction with signs. So if we made the applied force to the right positive, force of friction to the left will be negative, and it's negative, so it's 30 newtons. So plus negative 30 equals mass times acceleration, 10a. So 100 plus negative 30, so 70 net newtons of force, because friction canceled out 30 of the 100, is going to be responsible for this 10 kilogram mass accelerating. So at this point, pretty straightforward, divide both sides by 10, and your acceleration for this box is 7 meters per second squared. All right, Raiders.